All right, so the purpose of this video is just to introduce a concept, a definition, I suppose, an object, let's call it that. So we're trying to come up with a definition for this particular object, which, is going to be an object that we're going to study quite a lot about. So this object is called a vector space, and here's the thing. There's no sense getting super beat up over these particulars. You're never going to be asked to memorize these. You're never going to have to reproduce all of these. This is just to say, we are coming up with a legal definition of what a vector space is, and here's what we're going to say. We're going to say that if we have collections of objects that satisfy these 10 things, then it's a vector space. And if you don't satisfy these 10 things, then you aren't a vector space. So let's get an idea of what we're talking about with a vector space. So to be a vector space, you first have to have a collection of vectors. So we're going to use capital V to refer to that collection of vectors. You could think in your mind's eye, like the standard column vectors, you could think of those as being a collection of vectors. So say, okay, put our foot down and say, let's deal with column vectors with 4 entries. Throughout this entire definition, we could think of our column vectors as being vectors with 4 entries. Now, you also need a field of scalars. Now, what is a field? Nothing to get too beat up over. These are just numbers that every number in this set has a negative, and every non-zero number has a multiplicative inverse. So examples of field of scalars and what we frequently use are the real numbers. So any number on the number line has an opposite. Any number on the number line other than 0 has a multiplicative inverse. So that's a common field of scalars. You could also talk about the complex numbers, like introducing the imaginary number I to talk about the field of scalars. But for our sake, let's just focus on the real numbers as our field of scalars. So any number off the number line is considered a scalar. Any object, for the sake of our talking here, with a column with 4 entries is our vector. Okay, but of course in general, let me just make a remark. A collection of vectors could be something other than a column of 4 entries. It could be a column with any number of entries. It could actually be other objects that we'll see through example. But now here's the idea. Vectors can be added to vectors, which is to say there has to be some way to take those 2 vectors and add them together to get something. And as well, there's got to be a way to multiply a scalar times a vector. So if you're given just a good old-fashioned number and you're given a vector, the number and the vector have to multiply in some way. Now, if you have a way of adding vectors and if you have a way of multiplying by scalars, then you are a vector space if these 10 things hold. And as we go through these 10 things, each of the things with an arrow over them, the U, the V, and the W, these are going to be vectors from our vector space. And the C and the K, the things without an arrow over them, those are going to be good old-fashioned numbers from our field of scalars. So our field of scalars, remember, as we can think of it, maybe in a concrete example, would be the real numbers, and the vectors could be column vectors with 4 entries. You might wonder why we use K here for the field of scalars. I mean, C is common because that's a constant. The German letter for constant starts with K, so C and K tend to be common. Germany has a rich history of mathematical tradition. So, okay, so let's go through these 10 things that every vector space must have. So first off, when you add 2 vectors, you've got to end up with another vector. So in other words, there's no way to add 2 vectors and end up with something that is not among your collection of vectors. When you add 2 vectors together, you should end up with another vector of that form. And think, with column vectors with 4 entries, you add column vectors with 4 entries, you get something back with 4 entries. That would hold. This is called closure of vector addition. Frankly, the labeling of this is not important, but what is important is to be a vector space, when you add two vectors, you have to end up with another vector back in return. What else has to be the case? Whenever you add two vectors, the order in which you add the vectors shouldn't matter. So we call this commutativity of vector addition. Again, the word commutativity, not so important, but the idea is to be a vector space, when you add vectors, order that you add shouldn't matter. Also, the way in which you add three vectors together, whether you add the first two and then the third, or the second two and then the first, shouldn't matter. So the vector addition should associate. Where you put the parentheses shouldn't matter whenever you're just adding up a collection of numbers. So the name is not important, but here's the idea, and something that we can always crutch on, is that whenever we're dealing with a collection of vectors, those collection of vectors, when we add up three of them, it shouldn't matter which two we add first, we should always get the same result. Okay, fourth, there should be a zero vector where no matter what scalar you multiply by the zero vector, you'll get the zero vector back in return. And if you think about the example that we were talking about, which is using our real numbers for our scalars and using columns of 4 entries for your vectors, there is a zero vector there, zeros all the way down. And if you multiply any constant times that column of zeros, distribute the constant to all 4 entries, you would still get the zero vector back in return. So there has to be a zero vector in your collection of vectors for it to be a vector space. What else must there be? There must be existence of opposites. So for any vector v, there's got to be a vector that's its opposite, which adds together to be the zero vector. And if you think, that also holds for column vectors with 4 entries, because take the column vector of 4 entries, take another column with the opposite entry in each. When you add the two together, you'll get a column of zeros. Also, closure of scalar multiplication. Take any scalar. Take any vector. When you multiply, you should end up with another vector back in return. Never should you be able to multiply a number times a vector and get something that's not a vector. In the case of the real numbers and our column vectors, this holds, right? Because you take any real number, you multiply it by those 4 real numbers, you'll get 4 real numbers back in return. Something else that has to hold, we need the distributive property whenever you distribute across a sum of vectors, which is to say if you take a constant and distribute it to a sum of vectors, that's the same as distributing the constant to each vector and then adding. And if you think about it, this holds for our column vectors, right? Because if you add 2 vectors together, what will you get in each entry? You'll get like the first entry plus the second entry, the second entry plus the you'll get the first entries added, the second entries added, the third entries added, the fourth entries added, multiplied by your constant. The constant would distribute through. Same thing here. If you took your constant times each entry, that would add up as well. So the long story short is this property would hold for our standard case. We also need to have distributivity of scalars. So note this is a different statement here. Now we have 2 scalars multiplied by a single vector, and this should be equal to the first scalar times the vector plus the second scalar times the vector. This should also hold. And I tell you what, as I was talking through 7, let's just see this in action. This is a constant times. What's the sum of the 2 vectors? u1 plus v1 down to u4 plus v4, right? Here is your sum of the 2 vectors multiplied by the scalar. And what would you get on the other side? You'd have c times u, that would be cu1 down to cu4, and here you would have cv1 down to cv4. Note, the left-hand side and the right-hand side are equal there. So in our case, with the column vectors with 4 entries and the real numbers, this satisfies property 7 as well. What about property 8? I claim this also holds. Take a sum of 2 numbers and multiply it by your vector v1 through v4. You know what's going to happen. You're going to distribute the c and the k to each of the entries in the vector, and this should give you the same thing as taking cv1 down to cv4 and adding kv1 down to kv4. And indeed that works out, right? Because whenever you add these 2 vectors together, in the first entry you get cv1 plus kv1, and that's precisely what you get on the left-hand side. And down in the last entry you get cv4 plus kv4, precisely what you get on the left-hand side. What else do we need in terms of our vector space to be a vector space? We need the scalars to associate, which is to say, if you're multiplying two scalars times a vector, it shouldn't matter whether you multiply the scalars and then multiply the vector, or multiply the scalar times a scalar times a vector. You should get the same thing back in return, and this should make sense with our example, because imagine two numbers being multiplied by your v1 down to v4. When you would multiply, you just take each entry in your vector, multiply by ck, and over here, if you took the c times kv1 down to kv4, you would get the same thing back in return. So the long story short is, our example of the real numbers and a column of 4 vectors satisfies this property 9. Here's the thing to think about though, we're gonna come up with a bunch of examples that are different from the standard examples that still satisfy all these properties. What's the last property that vector spaces must have? The last property is that if you take your number 1, note this is not the one vector, this is the one number, this is a good old-fashioned number 1. Take the number 1 times your vector, you should get the same vector back in return. And I mean, in some sense, that makes perfect sense, right? Because if you take the number 1 and you multiply it by a vector of 4 entries, you would take that 1 times the 4 entries, you get the same 4 entries back in return, and that would work. So, in other words, in order for a vector space to be a vector space, when you multiply by 1, you have to get the same vector back in return. So, what is the long story short on this? The long story short on this is when you have a collection of vectors, and when you have a field of scalars, we often use the real numbers. If there is a way to multiply scalars by vectors, if there is a way to add vectors to vectors, and all 10 of these properties hold, add 2 vectors, you get another vector. The order in which you add the vectors shouldn't matter. If you have 3 vectors, the order in which you add the 3 vectors shouldn't matter. There needs to be a 0 vector, which multiplies by any scalar to be the 0 vector. There needs to be opposites of every vector, so that the vector plus its opposite gets you back to the 0 vector. You need to be able to multiply any vector by a constant and get another vector back in return. You need to be able to distribute across a sum of vectors, distribute across a sum of scalars, associate the scalars in any way, and multiply by 1, the number 1, to be the same vector back in return. If you have those 10 properties, you are a vector space. If you don't, you are not. And let's go through some examples to see this in action.